Oi, pessoal. Nós teremos o Yago apresentando hoje, tá? Bem-vindos à reunião de partículas e astropartículas. Deixa eu só... Aguardem um minutinho aqui que eu vou mandar o link para todos. Como é que eu vou enviar esse link aqui? Espera aí. Pronto, já está ao vivo aqui tranquilamente. Pode vir, Yago.
Ok.
Tá, é só clicar aqui, tá? E depois ir no tela cheia, tá bom?
Ah, pronto, ok.
Beleza?
Pode começar. Só botar logo aqui no tela cheia. Full screen mode. So, hello everyone. My name is Yago. I will present this presentation about field theory. So, let's begin. To start, I will do a very fast review of the Newtonian way and the Lagrangian way to do physics. So, when we see a pendulum, the pendulum only moves, and we physicists try to understand the movement. So we made up a coordinate system and abstract.
Just a second. You have to present it.
Oh, okay.
Let me see. Share screen.
That's important.
Let's see.
Very fast review.
Okay, now it's open.
Dá aquela atrasadinha.
Okay, now it's open.
Obrigado. Good. So we made up some abstract concepts as coordinate system and vectors to do more loud. Okay. To understand that movement. And the Newtonian way to do physics is this. We do the vector analysis and find the net force, and using the second Newton law, we can find the equation of motion, and resolving the differential equation, we can find the function that describes the path that the trajectory makes. But we have another way to do such problems in a more elegant way, is the Lagrangian method. So we can we want to find the function that depends, that spatial function that depends on time, and we define another function called the Lagrangian. And that Lagrangian will be defined as a scalar field, a scalar entity. So we don't have to worry about the vector analysis. And we define the action, and using the Hamilton principle, we will find the Euler-Lagrange equation, and resolving that Euler-Lagrange equation, we can find the same equation of motion that we arrived using the Newtonian way. But using this method is more efficient because we don't use vectors, so it's more easy to do complicated systems. And with that idea, I will develop the field theory. So I will not find the spatial function in this time. I will find a field. And that field depends on the position and the time. And to simplify the situation, my field only depends on one spatial coordinate. But sooner I will generalize, extend that concept to 4 dimensions. So I will define a Lagrangian density that depends on that field and the partial derivatives. And the Lagrangian will be the integral of this Lagrangian density in space. So the action will be defined in that scenario. So I will only will bring a brief idea, the demonstration of the extension of the Euler-Lagrange equation using the Lagrangian density. So I will define a field that will be my stationary field. I call my phi s. That field, when I put in the Lagrangian density and put in the action, when I compute all this, that arrives in my minimal value of the action. So that will be the field that I want to study. So I will define another field that is a tiny perturbation of my stationary field. And that field will be my stationary field plus a tiny perturbation and a generic field, beta, that has to obey the boundary conditions. So when I put that phi epsilon on my Lagrangian density and compute the action, I will find a function that depends on epsilon. So to find my stationary function, excuse me, my stationary field, I only have to do the ordinary derivatives of the action. And sparing you of the guard details, using the chain rule and some 2 or 3 pages of calculus, we arrive in the extension of the Lagrangian equation using that notation. That will be my Euler Lagrangian to the Lagrangian density to study my field theory. So I can, but this case is only on one dimension. My field only depends on x and time. But when I extend this to 4-dimension space, to 3-dimension in 3-dimension space coordinates, my Lagrangian density will be more complicated. My Lagrangian and my action will be complicated as well, and the Euler Lagrangian will become that monster. So to shorten the notation, I can use tensors. So my space time I can notate using that symbol, and using the 4 gradient I can shorten even more the notation of the Lagrangian density and my other entities. So my Euler Lagrangian equation will become this. Let me hide this. Okay, and that I can use my 4 gradient in 2 ways here. And to be more precise, the time derivatives have the 1 over c to make the consistencies of the unities. But I have that derivative here and down here. So the factor 1 over c will be cancelled out, because I don't use c equals 1 because I think it's madness. Okay, but now I will arrive in the Klein-Gordon equation that will be the core of this presentation. I will define my kinetic density energy in such way, and my potential energy in that way, using this kappa that will be a parameter that will depend on my system. And using that, my Lagrangian density will be only the difference of my energies, and it will be that function. And when I plug the Euler Lagrangian equation in that scenario, doing some calculations, I arrive in that equation. And if I can isolate that kappa, I find this, that will be my Klein-Gordon equation. And that equation is very similar to the equation that we already know. That is the wave equation. Is pretty much the same, but is equal to 0. So my Klein-Gordon equation, it seems like a generalization of my wave equation. And using that idea, I can take a guess that the solution of my wave equation also is a solution of my Klein-Gordon equation. So I try to do that test. So I will let my function will be my wave, my plane wave solution using the complex exponential, and I will plug the Klein-Gordon equation and see what happens. So I do the partial derivative in respect of x, and do it again to arrive in that function. Because of I squared is -1, I can arrive in that link. So when I do the partial derivative over time, I arrive in another result. And when I plug all together, I arrive in that final link. If my field is a wave, is behave like a wave, my kappa has a physical interpretation that is connect with the omega and the k of the wave parameters. And here we have a little trouble with the notation, because here is the k of the wave parameter, and here is the kappa of the Klein-Gordon equation. But it's happened. Okay, but I can apply more physics here. I can use quantum mechanics, and using the plane wave equation of quantum mechanics that is proportional to that exponential. So I can rewrite the k and the omega with the respect of the momentum and the energy of a particle. So if I take that final link here and using the quantum mechanics solution, I can rewrite the equation of energy and arrive in that expression. But I can use another link to physics. I can use relativity and take the definition of energy in relativity of a particle with a mass m and a momentum p. And to make a consistency in these two theories, I can manipulate my quantum mechanics expression and arrive in that other scenario. So to consistencies, that kappa, h bar, and c has to have some meaning of mass. So that Klein-Gordon equation can describe a field that can describe a particles with mass m, and that have a connection with my kappa. So I can rewrite the Klein-Gordon equation. I can go back here and switch the kappa to more physical parameters: the mass, the speed of light, and the reduced Planck constant. And this solution, this equation, is only happen on a field that depends on one space dimension. So I can expand this to a 4 space dimension. And to clean the notation, I can use the Labertian that condensate all this information here in this tiny equation. And that equation I can use to describe particles with no spin and mass m different from 0. And that's my presentation.
Okay. So any questions? I do have. Yeah. So I let me just try to summarize what Yago said. Okay.
Okay.
So let me see how we're gonna do this. Let's see if I can improvise. No, if I do this, you'll remove there. Just a second. No. Yeah, how I'm going to do this? I should have brought my table. Which is the table? So how am I going to do this? Because I want to explain the board. Obviously. Okay, so let's do the following. I'll let Johan start. So, do you have any questions so far, David?
Oh, some comments about your presentation. I really enjoy it. Some things have to be commented here for the all right. The first thing is the thing is important to understand the necessity of the Klein-Gordon equation, because Schrödinger equation is not Lorentz invariant, so it's important to comment this. Okay. And you need a theory that is Lorentz invariant. So Schrödinger equation, the wave Schrödinger equation, not the quantum mechanics fundamental Schrödinger equation. All right. And the second, this is important, and you talk about quantum mechanics, but that is classical field theory, not quantum mechanics field theory, because in quantum mechanics, space is an operator, not a coordinate. Okay. And this is something important to understand when you're talking about field, because in a field quantum mechanics, position is not anymore an operator. This is weird when you pass from quantum mechanics and quantum field theory. So I think it's two important comments. And if you calculate the current, you find something very weird. I try to calculate the current. You will find states of negative energy. Try, and you will find something weird. All right. And because of that, Klein-Gordon equation was dropped off for a long time, but Dirac and their interpretation bring it back. I think it's that.
Thank you.
All right, so let's do the following. Yago, could you hold this for a moment?
Yeah.
Okay, I'll explain to everybody. So let me try to summarize what Yago explained, okay? So mostly for the beginners. So every field, whether it's a scalar, a vector, or a fermion, has to obey some equation. Every field in the universe has to obey one equation. So the one that dictates the scalar field is called Klein-Gordon equation. This one that governs the vector equation is called.
Stop to share that screen. It's better for someone
Yes.
watching.
Oh.
Thanks. Sorry, guys, we are learning.
What? You're not getting
Yeah, that's much better. No, you can see from here. Look in here. Come here, Yago.
Oh,
Yeah, you can see there. So let's see. Then this thing.
yeah.
Doesn't have to share. All right. So we're trying to do our best. Okay, that's the Broca equation. And that's the Dirac equation. So this one that Yago was focused on is written as, can you read it? So I won't write that part. It's written as del mu 5 minus n squared phi squared. So that's the Klein-Gordon equation. I know it from off the top of my head, just because I'm used to this. And the same for the Broca equation, which is called box a minus n squared a mu equal 0.
So you cannot put Lagrangian in the left side if it's equal to 0.
Yes, that's why and the Dirac equation, I'm gonna erase this. It's written as sum bar E mu minus psi. So these Lagrangians, this one governs fermions. These Lagrangian is scalars. And this one, vectors. And what the main message that Yago was trying to present was, every field has to obey some Lagrangian. So eventually those who are young, for those guys who are much younger than some of us, you're going to learn eventually that from the Lagrangian, you can get equations of motion. Like, for instance, you learned that from early on that second law of dynamics is force is equal mass times acceleration. But you can get some of those results from Lagrangians, okay? Using Euler Lagrangian equations. So you have a Lagrangian. From the Lagrangian, you use the Euler Lagrangian equations to derive the equations of motion. So it's afterwards. So you have the Lagrangian, later you get the equations of motion. The same way Ricardo obeys force equal mass times acceleration times A, scalar fields should obey this Lagrangian, vector should obey this Lagrangian, and the fermion should obey this Lagrangian. Every field in nature is one of these three. Okay? Every one of them. An electron. An electron is a fermion, so you should obey this equation. Okay? A vector boson like photon, which is light, or some bosons which explain strong forces and weak forces, they are governed by this one. If they have mass or not, you just put m equals 0, and that's what you get. So if it's a vector, what is a vector? Vectors are particles that mediate or are messengers of some forces. Like photon is a vector. W and Z bosons are vectors. They mediate the weak interactions, so radiative decays. And there are gluons, which are also vector, and they mediate the strong interactions. So the ones that put atoms together. Okay? How nucleus are formed together, they are tied together, they do not disrupt. This is explained by the strong forces. And the mediators, the messengers of the strong forces, are the gluons. The only difference is that these guys, gluons, are not massive, so this thing is 0. The same goes for photons.
Yeah, it's working.
Yeah, but it's okay. But it's not just not here. Whatever. For photons and gluons, this thing is 0. But for massive bosons, this thing is not 0. That's the only difference. If it's a fermion, it's this. An electron, a proton. The proton is more complicated because this Lagrangian is for point-like particles. For point-like particles, that's the Lagrangian. If you have a particle which is not a point-like, this thing gets a bit more tricky. Okay, so electrons, muons, neutrinos, they all obey this Lagrangian. Okay? For now, what is the Lagrangian for the electron? This one. For neutrino, neutrino is, let's say, approximately massless. So it's this one. What else? That's it. Nothing else changes. So the Lagrangian is the same. Okay? All right, but there's a whole different thing about that concerns about how these particles interact with the matter. How electrons interact with matter, how an electron, if it passes an electron and a positron, how we do interact with each other. This thing is governed by the Lagrangian. Everything is governed by the Lagrangian. And how, for now, but I don't know how to write them in Lagrangian. I'm supposed to write one. I can write mine one, Lagrangian Farinal, Lagrangian Picard, Lagrangian. That's not how it works. There are some laws of nature which you have to obey. You have to obey. I will give you one that everybody knows, even the undergrads. Electric charge is conserved. Okay? Everybody agrees with that. And there is a law of nature behind this. So this law of nature sort of tells us what kind of Lagrangian I can write down. I cannot write any Lagrangian. I cannot write a Lagrangian where I have positron and another positron, for instance, and that's it. I cannot write a term which has positron and positron here, because this violates charge. It has to be a positron and an electron together, because the charge of this Lagrangian is neutral. Lagrangian does not have charge. That's why I have psi and psi bar. So particle and antiparticle together, always, because charge is conserved. This one is simple, but there are other ones, and makes this Lagrangian much more complicated, right? But obviously, you learn this in a 6 months course. Okay. So I won't be able to explain this.
But for now, when you study quantum field theory, the real reason that the conservation of charge is a consequence, not an imposition. Because if I remember well, is psi bar in this because have to be Lorentz invariant.
Right, but you want
conservation is a consequence of a current that are create automatically in this situation.
I know, but that's the point. We write the Lagrangian in such a way that at the end of the day, I have the electric charge. So I can just say, it just happened by accident that the electric charge is conserved. No, you write in such a way that the electric charge is conserved afterward.
But I understand your point, but it's a natural consequence of Lorentz invariant because
No,
when
because
you build this field, you find the number operator. If this number operator is automatically conserved by Nether's theorem. So
Yeah.
if it's Lorentz invariant, automatically obey conservation, charge conservation. So charge conservation is not some fundamental physically. Is a consequence of Lorentz invariant theorem.
No, Lorentz invariance does not guarantee electric charge conservation.
What field do you know that broke this law? Because I don't know.
No, friends, we have the standard model, right?
All right.
So the standard model group has SU2U1.
All right.
When you break SU2U1, you get electric charge, right?
Okay.
Because I wanted electric charge. So SU2U1 is the group because I wanted an electric charge, not the other way around. So first I want to preserve electric charge. I know that electric charge is conserved, not because I want it, it's because that's nature.
But in this point, for example,
but that's not,
you do not put do not put electric charge in this moment.
Right.
But I can prove that has an operation, the number operation, and any field that is proportional to this number operation is conservative.
Right.
This is very direct to prove.
Yeah.
And for some reason, the mysterious of the nature, electric charge is the same form. So,
but you right, David. But this Lagrangian is only meant for undergrads because this Lagrangian does not exist in reality. What you have is this thing, but how am I going to explain this thing to these guys? I cannot explain this to them. They thought it's just a change from small d to a capital D. But this, there's a whole story behind this. But even Yago, look, Yago says, what are you talking about? It's just changing D from capital D. But believe me, there's a whole thing behind. But, okay, so this Lagrangian, sure, you're right. It does not guarantee electric charge is concerned. Sure. But this is not the real life. So you have to come from a group, but I cannot explain this to them yet.
But my point is another, because when I study quantum field theory, they have fundamental laws. For example, the fundamental group is Lorentz invariant group. So I never saw a Lagrangian density that was not a Lorentz invariant that does not conserve charge. So who is the fundamental thing?
Friends, there are theories beyond the standard model where Lorentz invariance is broken, but the electric charge is still conserved.
Right. I never saw it. It impressed me a lot.
One of them, which was your former supervisor, works on this.
Because my theory broke in my master degree. My theory broke Lorentz invariance, but even conserved charge, because I proved that in this theory has a current that conserved probability charge.
Right. So
and
it's the opposite of what you said. Lorentz invariance does not imply electric charge conservation. Does not. That's what you said, right? It does not. It does not.
Right.
It does not. So Lorentz invariance does not guarantee electric charge conservation, or vice versa. It doesn't. But in the standard model, it does. All right. So I guess that's what it is. That's it for you guys. So we finished with the undergrad meeting, and now we're gonna have the postgraduate meeting with Johan, future Nobel Prize winner. Johan, here it is. See? A guy who works out at the gym.
All right. Well, I am going to talk about today invisible particles. These are the principal thing that guys studied in this paper. In a specific decay. This decay is very important to test beyond the standard model, physics beyond the standard model. So it's important to see that invisible decay don't have experimental results. This is the main idea. But we have from the standard model, we have a value that you can see. In the standard model, we have the branching ratio of that invisible decay that the neutrinos are the invisible particles of the standard model. We have approximately 10, 10, 10. This is a value very super, very a small value because the branching ratio, or specifically the decay rate, is proportional to the mass of the neutrino. In the paper, they call that term as well. It's a
So just what he's explaining, so let me give you some background. So he's talking about this because if you have, let's say, let's try to be as simple as possible. Let's say Yago is a new fundamental particle in nature. And he's very light. So what happened is the Large Hadron Collider, the famous one, is very hard to find Yago because Yago is light. These big collider machines are appropriate for heavy particles. If you're a light particle, sorry, you hide under the events. It's very hard for a big collider to find light particles. There is a whole story that I will not dwell on this. So I will not prolong my explanation. So how I'm supposed to probe the existence of Yago? The LHC cannot probe this because it's not an appropriate collider for this. For heavy particles, for having, let's say, a new fundamental force in nature, and this new force is Yago. Yago is light, I cannot probe Yago at LHC. So how am I going to probe this? One way is to search the presence of Yago, of a new force, in decays of mesons, in meson decays, such as kaon. Kaon is a meson which decays into neutrinos. Neutrinos are known as the ghost particles in the scientific books. Are particles that you very light and very hard to detect. So a kaon can decay into neutrinos and might also decay into Yago. So now I say I have an experiment that precisely measures the decay of kaon into neutrinos, or kaon into whatever is light. I say, okay, so the probability of a kaon decaying to a very light particle is 10 to minus 10. That's 10 to minus 10. So I say, okay, Yago, if you are there, your number, the presence of Yago has to be within the error bar. Within the error bar.
Can you repeat this part, please?
Yes, hold this for me. Hold on. So, just a second. So let's say this is 10 to minus 10 plus minus 10 to minus 11.
All right. I understand what you're saying.
So this is the error bar inside this number. So if Yago is present, Yago contribution has to be as large as this number, because that's my error. I don't know how to quantify this number. So it cannot be 10 to 10 because I measure it's 10 to 10, 10 to minus 10. It cannot be larger or smaller, but at least this amount. Okay, so it's one digit, let's say, compared to this one. So okay, now this is the error bar, and then say, okay, if Yago is present in K on the case, the branch ratio of Yago, the contribution of Yago to the KM has to be smaller than this, or at least as large as this number. And then that's how I constrain the presence of Yago or any new light particle in nature. But that's general. It's not just for Yago. It could be as light as someone who is thinner, let's say, David. Any part, all right?
All right. So that is the theory. That is the results of the standard model, because we don't have experimental results to relate to that value, right? So if we have beyond the standard model that predict like a value predict times 10 to minus 10, we have a proof of beyond the standard model, the physics beyond the standard model. So this is the main idea of the paper, because the authors use another experimental results related to chaos, another type of chaos, charge chaos, to test beyond the standard model using three types of gauge models. We have here 2 Higgs double model. This is the first model. The second model is 2 Higgs double model plus a small Higgs. And the third is mirror model, right? So the first thing is, in the standard model, the first model, in the 2 Higgs double model, we use specifically Lagrangian, effective Lagrangian to test the decay, because we have k on 1 is 2.
And one thing, I told you to not be pedagogical, because this section of the group meeting is meant for postgraduates. Okay, so that's why he's not explaining the whole details, because you arrived late. So we started earlier. Okay.
So in the standard model, we have the effective Lagrangian that we call effective standard model. But we have this scale. In that Lagrangian is valid, we have the quarks that are inside of the chaos, down quark, strange quark, and the neutrinos that are all invisible particles of the standard model. So with this Lagrangian, we can show an equation that is really large, but
Okay, so skip the equations, go straight to the results.
this is the result. This is the result because the decay rate is proportional. This is the main idea, right? It's proportional to a constant that depends on the mass of the particles that we know, but it's proportional to the scale of the energy of that effective theory. But in the 2 Higgs double model, if we use the a calculation of the branching of the decay rate, that calculation is proportional, but in this case is another type of chaos, a charge chaos. is proportional using the invisible particles is proportional. A constant that depends on the mass of the parent, that we know the value of that mass, the mass of the neutrinos, and proportional to the energy scale of the theory. So with that, we know the experimental value, the branching ratio of that decay of the charge chaos. We know that value. So the idea in all the models of 2 Higgs double model, 2 Higgs double model plus the little Higgs and mirrors, mirror dark matter models, is that we can relate an experimental value, the branching ratio of the long chain, the invisible particles, and the branching ratio of the charge chains, and relate that to values. We don't have experimental value for the long chains, but we have experimental value for that particles, and produce a value, a number, right? So we can, using that experimental value, to generate a number of the branching ratio of the long chain. Let me see, they could be that -1 times that value, right? So with that, we can a number for the branching ratio of the long chains, and they prove that that value is greater than 10 to -10. So this is the proof of physics beyond the standard model using 2 Higgs double model, and the same thing is done in the other models, right? The 2 Higgs double model plus little Higgs and mirror models.
All right.
Basically, this is the main idea.
So thanks, Johan. So the key thing is, in some models, it's easier for you to have a new physics signal at meson decays than at LHC. So it's not that LHC, the Large Hadron Collider, is the best probe. No, it's not the best probe for new physics. It depends on the model you have. As I said, for light Yago, it's not. For light particles, it's not. It's not. So there are other detectors which are much cheaper. Let's say LHC budget is, a few billion euros. Okay, and their detectors, for instance, to measure something like this, you take a couple of million. I say, okay, but why am I gonna do this if I have LHC? Well, it depends on what kind of new physics you're trying to probe. So that's the main message. So, depending on the kind of new physics you're trying to probe, LHC is not the best detector. It's not. Okay? And that's well known in the community. All right?
Right. Questions?
And I also mentioned this because we are interested in these 2 Higgs double models. And the models that we are interested in, I don't know if I should say this live, because someone might get the idea. I don't think they will watch anyways. So in the models that we are interested in, people have not done this. So they have not constrained the physics beyond the standard model, the models that we're interested in, using K-1 physics. They have not done this. So it's a paper that maybe Johan will do eventually.
So,
all right, so let's applaud him. All done, all done. All right. So we'll try to do better next time. Bye.